In this video, I'm going to walk you through the steps of conducting a factorial between subjects ANOVA. So the first step, I think, is to check the level of measurement associated with the dependent variable. You may recall that it's supposed to be measured on a continuous scale, interval, or ratio. But I also mentioned in the textbook that you might be able to get away with a 5-point Likert scale because there is simulation research suggesting that the ANOVA works pretty well on such level of ordinal measurement. Now, once you've been satisfied with the dependent variable measurement on a particular scale that is appropriate, you can check the number of levels associated with the independent variables. Now, recall that in a factorial between subjects ANOVA, you're going to have 2 or more independent variables. You'll also want to look at the levels. And so that might be a 2x2 between subjects ANOVA, which is the simplest case of a factorial ANOVA. Or you might have something bigger, a 2x3, a 3x3. This is information you want to keep in mind because it will have an impact on the type of post hoc testing that you're going to do on the main effects. So if you have a main effect that's significant and you can interpret it, and you have 3 levels in that independent variable or one of the independent variables, you could consider doing a Fisher's LSD as the type of protection to keep your family-wise error rate close to 0.05. However, if you have more than 3, then you're probably going to be stuck with doing a Bonferroni if you want to be serious about protecting the family-wise error rate. Now again, this is about main effects, omnibus main effects that you might want to interpret. Now it might be complicated if there's a significant interaction. Now the next thing you'll want to do is check for normality and outliers. And I mentioned here that that should be evaluated for each group in the analysis. Do not simply calculate skew and kurtosis for the variables that are in your data file in SPSS. Instead, you need to break it down across the groups on those dependent variables in SPSS. And I show you how to do that in the textbook. Now, you could take into consideration the simulation research that shows that absolute skew and kurtosis of 2 and 9 is the absolute maximum that you should allow when evaluating this issue. And outliers, you can consider using the interquartile range rule with a 3.0 multiplier. Next, check for homogeneity of variance, and you can test that with Levene's, which is readily accessible in a program like SPSS. So if the Levene's test is found to be associated with a p.05 or greater, then you don't have any worries about violating the assumption. However, if the p is less than 0.05 and you reject the null hypothesis of equal variances, but you also have equal sample sizes across the groups, then you don't have any worries. Recall that with equal sample sizes, you can still violate the assumption of homogeneity, and the ANOVA will still be able to produce a p-value that is accurate. Next, if the p-value is less than 0.05 and you have unequal sample sizes, then you have trouble if you violate the assumption of homogeneity of variance, and I suggest here that as a solution to the problem, you can equalize the sample sizes using that random selection procedure that I showed in the textbook. I do mention here at the more advanced level that if the variance, the larger variance, is associated with a larger sample size in the analysis, then you might consider that the p-value produced by the ANOVA is going to be conservative, and therefore you might not have to do the random selection procedure to equalize the sample sizes. Again, I talk about that in the textbook. Next, once you're satisfied with the homogeneity of variance assumption, you can evaluate the omnibus main effects and interactions for statistical significance. So those omnibus effects are reported in the ANOVA table, that key table with all the f values and the p values and partial eta squared. That is where you're going to evaluate whether the main effects and the interactions are significant or not. Next, if one or more of the omnibus main effects are significant and you have a significant interaction, you're pretty much left having to conduct some simple main effect analyses in order to evaluate whether you can interpret the main effects or not. And in the textbook, I say that if all the simple main effects are statistically significant and in the same direction, then you can interpret the main effect, even if the interaction is statistically significant. Next, you want to consider effect size, and for the omnibus effect size, you'll be looking for partial eta squared, which is reported in that key ANOVA table. You want to report that for every effect that you report in the analysis. And for the simple main effects, you would consider Hedges G, it's sometimes called Cohen's D, for each of those analyses. Now finally, you would look at a graph for a between subjects factorial ANOVA, because that is the best way to help interpret an interaction. And you have the option of a bar chart or an error bar chart in this context, because that is really going to elucidate the nature of the interaction. So those are the 7 key steps associated with conducting a factorial between subjects ANOVA.